So good morning, everyone, and welcome back to the last day of this focus week. So this morning we have two final talks, and the first of them is given by Takashi Oka from neighboring ISSP, and he's going to tell us about driven chiral systems, novel quantum anomaly.
Okay. Thank you very much for the introduction. I'm Takashi Oka from ISSP, and I also want to thank all the organizers of this workshop for putting this together. And I also want to thank all the people who came this morning. Okay, so today the curriculum we talk is driven Dirac systems. Okay, so I have been studying these driven Dirac systems. It's like Dirac electrons driven by electromagnetic fields and so on. But I have this stuff. So, okay, today, in addition to Dirac systems, I also want to some topics related to interacting system, which is not really a Dirac systems. But I thought that it might be interesting for the audience today. Okay, so and then for big systems. So today I'm going to talk about two examples, okay, or two concepts. One, it's about the creation of particles in the vacuum. So you know that if you have an insulator and if you apply very strong field, you can get some air excitations. So I'm going to try to tell you that this microscopic mechanism of air creation, it is kind of related to non-Hermitian physics that we have also learned during this workshop. Okay, so dynamics in a closed system can be related to non-Hermitian physics. So that's one thing. The second topic is now it's related to driven Dirac systems. I'm trying to find a way to realize fragments in periodic drivers. And actually, we found a very nice example. It's a one-body example to do this. Next piece. So this is my outline of the talk. So I have three parts in my talk. 1, 2, 3. In the first part, so actually I'm going to start with a very historical topic. Actually this is the first, in my knowledge, the first example of research done for driven Dirac systems. So it's the work by Heisenberg and Weyl, which goes back to 1934, then to work by Schringer. So I try to explain how these research is related to more modern concepts such as Berry phase. And then after explaining this old work, then we try to extend this idea to two different directions. One, so these people, Heisenberg and Schringer, they have studied the creation from a free fermion vacuum, so the Dirac sea. But then maybe we can use the same concept to study excitations, non-perturbative excitations from some SPP phase. So many body interacting system with a topological order, very short range topological order. Then in let's see. So actually, Heisenberg and Weyl, they studied the situation with static electric field and static magnetic field. One can study effect of fields which is time dependent, especially time periodic, using the Floquet method. So using the Floquet method, in the past, many people have studied the effect of AC electric fields, so oscillating electric fields. This has been studied by a lot of people. But then we are trying to extend such ideas to AC magnetic fields, so oscillating magnetic fields. And then we also found some new type of Landau levels, so some fragments, which only exists in an AC magnetic field. Okay, so this is my outline one talk. Okay, so let's start one by one. Okay, so the first part is a review of the work by Heisenberg, Weyl, Schwinger. Actually, what they studied in today's terminology is very simple. They just study three fermions. So let's imagine that you have this Dirac bands, or the Lagrangian is just like this. It's just this three Dirac Lagrangian, where I have my electromagnetic field, which is described by this gauge field A nu, and you have this gap. The spectrum of this system looks like this. I have the upper Dirac band, the lower Dirac band, and a gap. And then you apply an electric field in a magnetic field. This. If you that this is static, then what would happen? Okay. It's very interesting. So there's a paper by Heisenberg and Weyl. Sorry, this was 1936. It's really before World War II. So the finding is very interesting. So Dirac wrote this very famous paper of the theory of positrons in 1928, and just 8 years after that, Heisenberg and Weyl, and actually at the same time, these two groups have studied a very similar physics, which is the effect of electromagnetic fields. Okay, so this is the first part of the paper by Heisenberg and Weyl. It's written in German, but still I can kind of understand what it is written. So it says, okay, consequence of Dirac theory of positrons. So if you have positrons, you get something special. That's the title. And then what they showed is that you can write this so-called effective Lagrange function, which they show some very complicated integral representation, something like this expression. Also, so here it says they have this field. So n square, something. So they call this critical field. Actually, this will be the critical field that the QED vacuum will. Okay, so this is a field about which, if you apply stronger electric field, this QED vacuum will be destroyed. So there's a breakdown process. There's a very intuitive picture. Okay, so this is a picture in the x-axis. This axis is x. This part is the upper band, and this is the lower band. And if you have a static electric field, this band will be tilted. So this direction is energy. So the energy will go up. Then this picture, so the electrons, okay, so the electrons are occupying this part. And you can see that the electron can penetrate through this barrier and go into this upper band. This problem is basically something very similar to what we learned in undergrad physics, like a one-dimensional potential problem, where you have a tunneling barrier and a quantum mechanical wave function will try to penetrate through the barrier to this side. This is their very intuitive picture. And using this, they explain that there's a critical field. Actually, this critical field, somehow it's now called Schwinger limit, where although Heisenberg and Weyl have discovered this first. Okay, then let's go to the next paper. There's a very famous paper by Schwinger, written in 1951. So the title is Gauge Invariance and Vacuum Polarization. And basically what they did, is the re-derivation of the work by Heisenberg and Weyl using his new method called proper time regularization. So he found a way to do these diagrammatics in a gauge invariant way. And again, he showed that this so-called effective Lagrangian can be written in a very compact form like this. Okay. So this is some integral. F is supposed to be the static electric field. This integral has a imaginary part. It's a little bit hard to see, but since this has some singularity in the variable S, you can do some core analysis and you get the imaginary part of this quantity, which looks something like this. So it's a summation of exponentials where I have f, the absolute value of f in the denominator and m squared in the numerator. Now, okay, so this quantity, exponential, this is now known as the pair creation rate of electrons and positrons. Or maybe I can have one more slide related to Schwinger's work. So in a more field theoretical language, what Schwinger did is to calculate something like a partition function with external electromagnetic field. And since this is a free fermion system and Lagrange is quadratic in the fermions, you can express the partition function using a determinant of this Dirac operator. And yeah, if you expand this Lagrangian, you can get an expression like this, where this lines, wiggling lines correspond to the external gauge field, and this solid line corresponds to the electron propagator. So we know that these lines correspond to something like a nonlinear response function of a system against electromagnetic perturbations. So for each wiggly lines, you associate a electric field or magnetic field, so E or B. So this corresponds to some the vacuum switching to E to B. If I write it in terms of this, if we expand this, the field expression is something like this. And you see that there's an E squared and H squared, E squared minus H squared, and E dot H. So these combinations are Lorentz invariant combinations of the electric field and the magnetic field. And one more very important physical meaning of this quantity is that if you take the derivative of this quantity, so this is the real part of the effective Lagrangian. If you take the derivative of this in terms of E, you get the polarization of the vacuum. So vacuum is an insulator. You apply electric field. The electric field will break inversion symmetry, and there will be generated polarization. You can simply calculate it just by taking the derivative in E. Okay. So in the condensed matter community, in the 90s, we have learned quite a lot from the work by Weyl about this geometric phases. Then people have developed the so-called modern theory of polarization, or a very phase theory polarization. So this is something known in the condensed matter community, where you can write polarization using the Weyl phase. The Weyl phase is a quantity where you have this eigenstate of the Hamiltonian. You take the momentum derivative and sandwich it. This is use the Weyl phase. You can also think that the k derivative is a conjugate the position of x. So this is something like a expectation value of x, the position of electrons. And if you integrate it, you get the polarization, how the charge is polarized. A more equivalent but more compact form of this expression has been obtained by Lesta, where he studied it. So this is an expression where you have a ground state, a many-body ground state of a system. So this is, and let's say this is an insulating system. And then you take the expectation value using this wave function of the ground state and sandwich this twist operator. the twist operator is operator where you have exponential and x on top of it. So this position operator. So again, if you think, so this x operator, you can think it in two ways. But first of all, if you just naively think that this is an exponential of x, then if you take the logarithm, you would get the x itself. So in some sense, this derivation, this expression, you get the polarization. Another way to think about this is x will switch the momentum. So this is a momentum shifting operator, and you compare the wave function and a wave function where you shift the momentum. So taking the overlap of this quantity is related to the polarization. Okay. Then actually this discovery was very important in the quantum matter community because actually this polarization turned out to be one of the baby version of the topological index. So if you have a one-dimensional insulating system with inversion symmetry, this polarization should be either 0 or 1/2. So you can, from this number, you can tell if the system is in a trivial phase or a topological phase. This quantity is also related to quantum metric, and also there's some relation to the Lipschitz-Matisse theorem because you're kind of shifting the momentum and basically you're kind of slowly changing your ground state and trying to see if that is related to other low energy state. But anyway, then I knew about this work and the work by Schwinger. But then, so it's very natural to think what is the relation between these two expressions. So Schwinger's vacuum polarization and the Berry phase theory polarization. There should be some relation between them. So actually, this is very easy to explain. So it turns out that this Heisenberg-Weyl Lagrangian that I mentioned, where it was calculated by Heisenberg, Weyl, and Schwinger, actually it's really just a very simple. It has a very simple analogous expression to the twist operator expression. So let's imagine we have a system, so some system with a static DC electric field. So I have an insulator. Let's say I have a Hamiltonian insulator, and I put this electric field, and the electric field is coupled to the position operator. So this would be a Hamiltonian of a system where I have a DC electric field in the potential gauge. Okay. Then let's imagine that I'm considering a time evolution with this Hamiltonian with the electric field. Let's try to write the time evolution operator in the interaction picture. So then the time evolution operator will look something like this. So exponential of this x hat, which is a position operator in the interaction picture. Okay, so basically, now you start to see that this looks like a Swiss operator. And you can show that by taking the adiabatic limit of this expression. So this is a ground state, time evolution ground state. So ground state to ground state transition amplitude and taking the logarithm. Basically taking the adiabatic limit of this quantity, you recover the same expression as this twist operator expression like this. Or it's nice. Then more generically, so this is an expression good for the potential gauge of an electric field. But if I want to study it in a different case, like a time-dependent case, I need a equivalent but different expression. And that's again the same ground state to ground state transitional amplitude. So I start from the ground state and just time evolve it by changing the parameter which I denote as gamma. So I'm just changing my parameter with lambda, and doing not just a adiabatic, but allow a non-adiabatic time evolution. And then I take the expectation value of that quantity against the ground state of the system at that parameter point. So this is a ground state to ground state transition amplitude. And then, so if you take the long time limit of this quantity and kind of normalize it, you get this density. So this effectively as a density. So yeah, it's a normalized quantity.
Sorry.
You go first.
So, Takashi, one question, is operator X is not exactly a gauge independent quantity, because you need to fix your coordinates, right? For that. So how do you do this in your this thing? Is there a convention?
Oh, so the expression of the Hamiltonian is not gauge invariant, but once you calculate this quantity, they will be gauge invariant.
No, but in the adiabatic limit, this depends on the operator X. And if I shift my X by simple translation, that would change, right?
Yes, it will change for time dependent expression. I will show it in the next slide. And it gives the equivalent result.
Okay, thank you.
Let me see a question. So in this Bristol formula, the coefficient 2 pi over L is a precise meaning because it means that if you go to L, then it's like doing no rotation. But in the case of this position operator, it has a continuous spectrum. It has no meaning.
Yes.
Saying TE equals 2 pi over L.
So that's so then when you take this adiabatic limit, you have to fix the end point of your time. So you don't really, you take infinite time, but then the phase that you shift should exactly agree 2 pi over L in this expression.
Yeah, but what does 2 pi over L has any meaning? Because you can always multiply, again, in this case, multiply your position operator by an arbitrary factor. But you cannot do that in the rest of the case.
Oh,
but anyway, probably this is
okay. Let's see. So my talk, the first part is based on a continuous model, so it doesn't have the lattice periodicity. Maybe that's related to it. Okay. So using this expression, okay, let's try to recover Schwinger's result using this expression. And yeah, actually this turns out to be a very simple exercise. So actually, it's something already well known. So the three-dimensional 3+1 with Dirac module in static electric field, there's a good quantum number, which is, of course, the momentum. So if you separate the system to each momentum point, and then you also have another good quantum number, which is spin, then the model reduces to the 2x2 Landau-Zener problem. So originally you have the Dirac, but at the end you just have the textbook Landau-Zener problem. This becomes exact in this situation. And the Landau-Zener problem is a 2x2 model where you have, as we can select, there's a way to select the parametrics. Let's say I have sigma x and a mass term, and sigma x and v cube, where Q corresponds to the momentum along the electric field. So now I have the momentum Q in the direction of the electric field. So this is going to move at the speed of ft because this is the gauge field in the, so this is ax, the gauge field in the x direction, which moves linearly in. If we write the spectrum of the Landau-Zener problem, have the lower band and the upper band. And then basically I'm going to evolve starting from the one of the eigenstates here and just to time evolution. My Weyl function will evolve, but there will be some tunneling process to the upper band. But So there will be a tunneling to the upper band, and there's some remaining in the lower band. This tunneling to the upper band corresponds to the creation of electron and hole pairs. But in the two-level problem, it's really just saying that my wave function will split into two eigenstates, adiabatic eigenstate 1 and 2, and the coefficient is going to be square root of 1 minus p with some phase, and square root of t with another phase. But then, if I want to calculate this transition amplitude, I have to just, this is from the ground state, so this one state, the one state. So I just pick up this component. Okay. So I just pick up that component, and then I just take the logarithm of it. So you see that, so if you just take the logarithm, you get this phase in the logarithm of 1 minus t. So this phase, the logarithm of 1 minus t. As for the real part and the imaginary part of my quantity, this quantity, or the electric Lagrange that I recall. Then, so what is this phase and the transition tunneling amplitude? According to Landau's textbook of the Landau-Zeno problem, I know the answer. So it is said that this tunneling complexity P is given by P is the square over F, where F is the speed, and the phase. We've written about the phase, but actually this phase is known for this Landau-Zeno problem, and it is known as the Stokes phase. And it has, actually you have to do some look up some literature, but you can show that this phase is can be written like this, some complicated integral expression, which start to look like the one that I showed in Schwinger's paper. Actually, so you still have the momentum. So this is done for each momentum points, one by one. So each momentum point reduces to a 2 by 2 two-level problem. But then again, I have to do a momentum integral of this quantity. But then if you do that, you recover the result by Schwinger.
Then, excuse me. So I'm a bit confused with the relation to the Schwinger result. Schwinger result is already momentum integrated. I see. But okay, this one is how say your formula is a momentum resolved at the
first momentum result. Or
I see.
Basically, these whatever. I think for these very simple problems, you have many equivalent different.
We also thought about the 3+1 t.
Yeah, also about 3+1 is correct. Thank you. Okay. Then one more step. So here I relied on Landau's textbook to show that this tunneling amplitude is this Landau-Zeno formula. But for more general problems, we want to have some independent way to calculate the tunneling amplitude. Actually, so there is a way, which also has a very long history, which is known as the imaginary time method, or Landau-Dihine theory, or DDP theory. First, this was developed by Dihine, a Russian guy, in 1962. Also, in the context of quantum chemistry, it has been used and developed by Davis and Edgeworth. But it's an approximate, but a very simple and powerful method. So what they was thinking about is to study a two-level system, a general two-level system, and try to evaluate its tunneling amplitude. They showed that, so this is the result. And what they showed that the tunneling amplitude can be written as an exponential of some integral. The integral is the energy difference of the two eigenstates, 1 and 2. But then the integral is done for the complex time. So this T prime, it's originally a real time evolution, but you do this time evolution to this complex time, which they call T star. At this T star, this is a T star, which is defined as the point where the two energy becomes the same fluxes. See, we know that this, in the context of non-formation physics, this is the exceptional point. So basically, you do this integral of this energy difference to the exceptional point. A very simple way to understand this is really you just write down the Schrödinger equation for the two-level system. Let's say the coefficient is A minus. So you can find this in a very nice paper by Fukushima-san in Nihongo, Fukushima and Shimadaki. They're trying to extend this the formula to more precise form, but they also have a review of this equation. So basically, you write down the expression of this is just a solution of the Schrödinger equation, and you see that there's a phase factor here. And then you have to do a very nasty integral. Okay, so this phase factor is the integral of this energy difference. So integral of the energy difference on top of an exponential, and then you still have to do this time integral. But then in the spirit of like WKB approximation or saddle point approximation, you can say that the relevant part of this transition amplitude will come from the point where this phase factor becomes the time derivative goes to 0, so where its value doesn't change so much. And that's precisely the point, not in the real time, but the time in the complex time. Okay, so that's nice. Let's interpret this in the language of the Dirac model, what we call Schwinger mechanism. Okay, so we were studying this very simple free fermion model with a static time-dependent gauge field and a static electric field like this. So this, using this imaginary time method, basically my time t will be extended to a complex number. So I would have a complex gauge field. So Dirac model with a complex gauge field, which is something like a Hadamard-Nelson-like model. And the important thing here is that this model has an exceptional point. Okay, so what's the exceptional point? So again, this is just a simple Landau-Zener problem. So I know that my energy difference is a square root of t square plus delta square. Sorry, I will put a minus sign here because my t is a complex number. Okay, so originally this is a plus t square plus and the delta square. But then I'm going to do an integral and I'm changing my t to complex t. And you find that there's an exceptional point here. And with the position of delta over f. So if you do this integral, you get delta square over f. And just plugging this into the previous imaginary time formula. Sorry, this font is not so good, but you recover this Landau-Zener formula. And then again, doing this momentum integral, you recover the result by Schwinger. Excuse me.
So as far as I understand correctly, the formula is approximated.
Yes, yes.
And but the Landau-Zener result is exactly what the Landau-Zener problem.
Yes.
But why is that?
Oh, it's a special example that this is accurate, but it's also approximate in a sense that the Landau-Zener formula is only exact if I do this integral from minus infinity to plus infinity. Then if I really try to limit my time or so on, then already this expression starts to become approximate stuff. But anyway, this is in the original Schwinger's calculation, the setup, it's really a minus to infinite, minus infinite to plus infinite integral. So it turns out to be exact.
And for long time I really don't know what is some underlying reason of the why is that so?
Why? No, I see. But that's the one can improve it, like the one but normally it will in this special model it will be the same.
I see.
Okay. So this summary of part one. So we have seen that this Heisenberg-Weyl problem, so static electric field, the tunneling production. So since we have this conservation momentum and spin, it reduces to a 2x2 problem, just a Landau linear model. And then there, the imaginary time method is accurate somehow. So we get this, at the end, we get this Dirac model with a complex gauge field. And we're supposed to study the exceptional point of that model. And then the information of how the energy approach to this exceptional point will give the tunneling amplitude. Also, I mentioned that this amplitude, ground state amplitude, will give the Heisenberg-Weyl electric action. Okay, so that was part one. Then let's try to extend this to a model of a many-body system. Okay, so this is a work mainly done by Koichi Okazaki-san. He's a first-year PhD student in my group. What he studied is we need to study instead of a trivial insulator, we want to study more complicated or more interesting insulator, which we thought that this AC-1 Heisenberg model is a good example. Okay, but this is just a simple AC-1 Heisenberg model with a static electric field. Again, we put a phase factor here and here, which corresponds to a DC electric field along the chain. We start our time evolution. So that I'm going to show you some real-time evolution using exact diagonalization. We start the time evolution from the ground state. The ground state is supposed to be in a state which is often picturized something like this. This is the valence bond solid ground state, which is actually accurate at the AKLT point, but for general Heisenberg model, it's only an approximate picture. But still, we have this picture. From an experimental point of view, this electric field is something like a tilted magnetic field applied to the system, which can be realized experimentally as well. Okay, then you can see in this plot I show you the current, spin current. So the electric field will generate current, and this is time, and this is the current, and you see the different color plots. So the weakest electric field is blue. So I would have this current which oscillates. This oscillation is a finite size effect. If I have a large size, this oscillation should go to 0, and I'll get a very flat current which is at 0. So system size is 8, it's very small. Then if I increase the electric field, so red, purple, green, and red, and you can see that the current becomes stronger and more and more. Okay, so what can we learn from this? Again, so one important thing, similar to what I showed in the Dirac model, is it's very important to see the adiabatic spectrum. The adiabatic spectrum of this Heisenberg model for finite size system is plotted here. So this blue line corresponds to ground state. Then I have some excited state, red, purple, and green. And okay, so it seems we confirm that during this time evolution, there's a tunneling from the ground state to the first excited state, denoted as this red part. So excitation from blue to red happens, where the tunneling probability will, I will call it P. Of course, there will be tunneling process. So once I go to this upper band, there's another tunneling process from red to purple, and maybe purple to somewhere higher. But here I just focus on this very initial process. Okay, again, this is just what I already wrote. So we already have this relation. So this gap system and its tunneling can be related to this non-permission physics, where I have this complex gauge field and then the exceptional points. Let's see if we can do the same for the Heisenberg model. So we are interested in this driven Heisenberg model, and I have this time parameter t at the phase. So if I make my time to be complex, then basically I'll just have a complex phase phi. So it's again something like a anomalous type model where my left and right hopping is different, has a different absolute value. Okay, so that's nice. Now, let's see what is again this relation that I use, this imaginary time method, is only an approximate method I mentioned. But let's just try this answer method. So this is an energy diagram of the lowest and the first excited state of the S1 Heisenberg model. And very luckily, we found the exceptional point. So this ground state and the excited state, the energy will merge here. Actually, this is at the center of this pi. Pi is from 0 to 2 pi over L. And at half of this period, we find this exceptional point. There's a point here. So this curve is related to the tunneling from this state to the upper state. Below the ground state looks something like this. So this VBS package. Excited state, we are not. So it's very, we wrote the paper, but unfortunately, we're not so sure what this target state is. One candidate. So we think that this target state is a tripron anti-tripron pair. So a state where you have around here up forming a tripron and a down forming a tripron. So this from the intuition we think that this is what we obtain, because we would have a charge here, positive charge and negative charge. The charge is like a magnetization, spin up here and spin down here. So this should be something pair creation. But actually, in the literature, we looked for some literature of the excited state of the AKLP model, but we couldn't find at this point this kind of excited state. Maybe yesterday there was a nice talk by Matsui-san, and maybe there's this state is among states. I don't know. Okay. Anyway. So this is almost just kind of this.
So for the excitation of the HLT chain, like if you just flip the local spin on half, if you just have a single flip, why do you think that's not the lowest excitation?
Yeah.
So here you're basically flipping like both kind of fractional spin on half. Why not just one?
Yeah, I don't. So since this is a singlet, I didn't know how to code. So you're saying spin up here and spin down here.
Yeah.
Would be a candidate. Maybe that's true. Maybe.
But it's almost the same as replacing the singlet with a triplet. So it's not a pair, but and this pair will go separate, right?
Yeah, this would be like a domain.
Yeah.
Domain 4, and it can be easily separated. So that's another equation.
So you expect that these two things will go in
Yes,
the
at the end they will go away. That's the
you now see kind of triplet going around in there.
Yes.
Yeah.
And at the end you form many triplet here and down.
It's plausible, but doesn't fit with what Matsui-san told us yesterday.
Excuse me, so I have to put with it. So, what is your boundary condition here?
In this, we did both. But this calculation is for periodic boundary condition.
But you just said some accumulated in the. But
If I do the emerging calculation with the open boundary, then
of
you
course,
go
yeah,
down and
right,
down.
right. But in this case, is you did the emerging or
This is just the exact time-oscillation with the 8 sites.
for periodic boundary.
Periodic boundary condition. Where I can write this kind of diagrams. So then I just show you this is almost final yeah. So actually using the same space so small, but what I brought here, you see circles against F. This is the tunneling probability that we numerically obtain circles. And then you see this red line, which sort of agrees very well for the weak field limit. Actually, this red line is it's a DDP, but it's actually this imaginary time expression of the tunneling probability where I use the information here. And in the strong field limit, it's a different story. So we have effective Hamiltonian from Floquet Magnus expansion. We will explain this. If you're interested, please have a look at our paper. Okay. You don't skip this. See, I similar. This is more. Just explain this in 1 minute. So see, similar calculation have been done in a long time ago. In the case of a 1D Hubbard model, and in the case of a 1D Hubbard model, we basically know the structure of the excited state and their energies, and the excited states correspond to string states. And the non-Hermitian extension of the string states has been done by Fukui Kawakami and Nakamura Hatao. And using the information with the energy in the non-Hermitian model, you can kind of precisely accurately calculate the tunneling amplitude. And you can write tunneling expression of the tunneling amplitude even from momentum resolved situation. And then you can apply for not just DC, but AC field or pulse fields. And this has been experimentally verified recently. That's one. Advertisement. Let's go to the last part. And since I don't have so much time, the equation is very simple. Okay. First of all, I'm going to return to my free fermion example. Just simple free fermions. Just simple Dirac electrons. So I showed you the result of Heisenberg and Euler. It's just static electric field. Then, some time ago, I studied a situation where I have a circular force that applied to the Dirac system. Then, this was very fruitful. There are many discoveries of topological phases created by circularly polarized electric fields. Then, more recently, we started to study the case where instead of the electric field, now the magnetic field is oscillating. So B is oscillating like cosine omega t. So what would happen there? That's why there's a very intuitive picture for this problem. Okay, so the big question here is, can we form Landau levels using oscillating magnetic fields? And let's think about this. So Landau levels, or you can say, think about cyclotron motion. Can we get cyclotron motions from magnetic fields that are oscillating, like E cosine omega t. Actually, the answer is yes. So so the magnetic field is oscillating. It's positive and negative, positive and negative. Let's imagine a process where my electrons. Okay, so I'm just solving Newton's equation under oscillating magnetic field. What you will get is that your electrons will form this kind of shape, this or this or this. Like if you have a closed orbit, the electrons will rotate right hand and left hand, right hand, left hand. Repeat this. So one period is right left. You get one closed orbit. This guy is actually right left, right left, right, right, sorry. This again is closed orbit. And then, yeah, you can extend this forever. Actually, you can even do quantum mechanics of this. You know that if you have a closed orbit and you do quantum mechanics, then you get a fragment. So basically, you get a quantum mechanical version of this kind of closed orbit, which forms a lambda level. So you can see this in this figure. That's nice. Then how about the Dirac particles? What's different from non-relativistic particle to Dirac particles? One thing is that you have electrons and holes. So this is my intuitive picture. This is yin and yang in the East Asian community. Yin and yang. So this is electron and hole, electron and hole, and hole. And in one period, the electron will do cyclotron motion. But when the magnetic field flips its sign, at the same time, if I can flip from electron to hole, I can continue the cyclotron motion. So I get a rotating cyclotron motion, where my feature changes from electron to hole and electron to hole. Okay. In more quantum mechanical sense, we get a gravity oscillation of electron state and hole state. Okay, so I will try to explain this in okay. Yeah, this is I will just skip this. This is like a introduction of Floquet theory. Sorry, I don't think so. Yeah, let's just see. So let's just study the Floquet the spectrum of a honeycomb lattice. Okay. Honeycomb lattice in oscillating magnetic field. Just to explain this and stop. So what we have is just a Dirac model with B cosine omega Tx. This is a gauge here, A, Y, in the Y direction, which is oscillating. So it will generate a magnetic field in the Z direction, which oscillates. You can do this in a lattice system using honeycomb lattice, and this is in a Riemann geometry, I get a spectrum like this. This is a momentum, which goes the Y direction. And in the X direction, I have a Riemann geometry, so I have an edge. Then I will crank up this oscillating magnetic field. 1, 2, 3, and so on. Okay, so you start to see some structure around here, which more or less looks flat. If I magnify it, you see this flat band here, which is separated by energy omega. Omega is this frequency of the external magnetic field. Okay, we call this flat band the π-Landau level here. You also see that the original Dirac band is preserved at this point. Okay, so then, okay, so this is a very complicated slide. But basically, so the question is, what is the nature? What is the intuitive picture of this high fragment? I already showed you that it's this yin and yang state. Okay, so actually you can obtain this mathematically or by doing very simple transformation, unitary transformation to the rotating frame. You can start from this oscillating magnetic field and use a rotating frame, move the rotating frame, and obtain a static Hamiltonian, which actually looks like a Dirac Hamiltonian in a static magnetic field. So, yeah, if you're familiar with the Dirac Hamiltonian with magnetic field, you will see it from here. But just please, trust what I will say. So the energy of this is the square root of B times M. And what we find is that the Planck function here is n equals 0. I would have n plus 1 and n minus 1 here, and so on. So there's a series of Landau levels formed around energy 1 over half omega, half omega. Now, this is the real space profile of these states, which actually corresponds to this yin and yang state. Or when pictorially, so it's a state which is a Rabi oscillation. So oscillation of between the two states. One state is basically a static Landau level or positive B. So it's like a electron Landau level of electrons. And the other one is a Landau level of hole, or a Landau level created by minus B. And then you just take this linear superposition with this oscillating coefficient. And then you get this kind of flat bands. And they have very interesting transport properties. So actually, if you apply oscillating electric field on top of this oscillating magnetic field, you will generate a DC current, which is a flow in the y direction. We call this heterodyne Hall effect. But I will just skip this. All this is all this has been done by Kiyamura-san in fundamental physics, and he has confirmed that the current that you obtain through this has a very universal form, which is very similar to the chiral anomaly, the CME effect. So this is my last time. I expect two things. This handling from the SDT insulator, and then physics in the oscillating magnetic field. Thank you very much.
Yeah, thanks for the interesting talk. So,
Thank you. I think it was very interesting. So I'm very curious about this. You're changing between electrons and hole. First of all, it looks like it's not allowed by charge conservation. But anyway, so how is this Rabi oscillation made? Does it automatically comes from this oscillating magnetic field, or does it come from something else?
Okay, so it's not really, it's really just a resonant state between the lower band and the upper band. So although I said it's electron hole, actually the charge itself is the same, but it's the lower band and the upper band. The wave function part is flipped. So whenever I have, this is already very common to Rabi oscillation. When you have two levels, up and down, imagine you have two levels, and then you have some oscillating field, which connects these two states. Then in the Rabi picture, you will have like oscillating wave function between the two states. In this case, one state is the lower band, and the other state is the upper band. So so I can write it into this.
Yes. So is this omega determined by this omega?
This omega is given by the external frequency of the oscillation.
Okay.
It's not it's not, if this was the time crystal, it means that this omega is induced by Dirac.
Yes.
Here it is given by the external field. So,
Takashi, very nice talk. Thank you. So just one question. To get this flat bands, do you really need to go to this rotating frame, or could you do this in Magnus few orders and then get this, or maybe it doesn't show up there?
this is applicable to this point, the low energy point. And if I do Magnus transformation there, actually I get something interesting related to this heterodyne effect. If I can do it. So if I have E and E cosine omega t, my Hamiltonian is like this and this, and cosine and sine. Having cosine and sine sounds a bit familiar. It's like having, ignore this x. Then it will be circular polarized light. We know that there's we can do Magnus expansion, and there will be gap opening here. In the same spirit, if I do Magnus expansion with this operator with x here, I actually would get this something E b over omega squared with the x. With x, this was the gap opening of the Dirac band. But now I have an x. So this gives a magnetic field, which results in a higher band, which will contribute to transport in the y direction.
Thank you.
Question.
For your discussion is two. It seems that in the so you use the Hamiltonian description, but if you use the path integral cooperation, it looks like what you're saying is connected with the existence of the complex saddle point, which is the path integral, and then there's instant dot.
Yeah.
So and then my question is that in that perspective, for example, so here you looked at the two neighboring bands which are close to each other, and that gives a leading contribution. But there are in general multiple bands, and then there are multiple complex saddles. And what you describe is a dominant contribution, but in general there is a sub-reading correction, and then it depends on the parameter. Sometimes the sub-reading correction jump, so that's known as the Stokes phenomenon. And then sometimes it jumps, so there's a phase diagrams. So that's a mathematical structure, I would imagine. I wonder if there could be any physics in that.
There's a very, very important and interesting thing. So indeed, in this model, actually we have higher bands.
Yes.
And it's not just one Landau's inner tunneling, but actually there's another Landau's inner tunneling here, and another, and so on, which will start to interfere with each other.
Yes.
And this is known as the Stokes phenomenon. So the Stokes phenomenon, also in the context of Landau's inner tunneling. In the language of this exceptional points, maybe it's a bit difficult to see, but already this down here, you start seeing, if you look at with your if you look carefully, you see some country. There's another band coming from above, which will touch around here. So in this kind of many-body Hamiltonian, there's multiple exceptional points happening somewhere near the real time and somewhere very far away from the real time. These will be very important information for the Stokes phenomenon.
I see. Thank you.
Also, okay, the context of singular. I think the paper by Fukushima-san, they say that this is related to Lifshitz sum.
Yes.
I think that's related to this passing zero. So they try to improve this formula from that point of view.
It's way to expand that to all those perturbation theory. That's not the exact WKB. So you use those formulas, I think you can
they are
We can make it more exact.
more accurate.
Questions? Yeah, I also have a few questions. So first, so in the beginning, you mentioned this Cresta formula for polarization and mentioned that it corresponds to the adiabatic unit. But I was still surprised because many different terminology that we also thought about this. And in our picture, this Cresta formula actually corresponds to potentially. Indeed, this amplitude actually vanishes even for gap system if dimension is higher than 2 or something. This can be derived using maybe the difference comes from the different gauge. So you took the potential time, set a vector potential to them. We somehow related to set up potential electric potential to them, but I use the vector potential.
Yeah.
And then we can derive that this Lester formula for the friendship. Maybe we can discuss more details later. And another question is that so in the beginning, you introduced this Schwinger theory or Heisenberg-Euler effective Lagrangian. One interesting feature I think is this imaginary part which corresponds to this creation has this essential thing like exponential something. Yes. But the real part has a table expansion e dot h and so.
Yeah.
So can you relate this real part and the emergent part by Kruma's code?
Yeah. Okay, so the relation between the real part and the imaginary part is given by Weyl dimension. And also in high energy physics, Gerardo Dune has been working on this for some time. For DUNME. I run it for their paper. There's relation. So if you have a series of expansion in F, you can do Weyl dimension. You can kind of recover the imaginary part.
Okay, thank you. So if there is no question, let's speak, right?